Well, okay, let's resume. So, okay, let's come back and restart and resume our journey here. So another important type of detection model is called YOLO. Basically, in the fast RCN, we have two stage, or in cascade RCN, we have multiple stage. So the idea there is we first detect one box and get their rough location, and then after that we will use those prediction to pull feature from the feature map, and then to get a refined prediction for the prediction for the bounding box again. So we can do this we usually do this twice, like in the two-stage method. But of course, people have been trying to do this only once, which is called YOLO. Basically, you only look once. So the model is actually simpler here. Given an image, so we know that again, similar to the previous case, we will first extract the feature based on certain downsampling, like downsample the feature resolution by 16 or something. And then instead of predicting the object location and then pull the feature, we will directly predict that for each location, what is the classification, and as well as what is the location of the bounding box. Basically, we say that for each pixel, whether it contains the object or whether it's the center of the object. And based on that, if it's the center of the object, what is the size of the object? So those are the two things we predict here.
Hello, hello. 1 2 3 4
Okay. Okay, so here are some more details. Probably you can look them up. But the idea here is we do this simple method. And the goal of this original method is actually not to beat the two-stage method. The goal here is to efficiency. The idea here is as long as we do not go to the second stage, and then we can use a simple model to predict both the object classification and object bounding box, then we can do this much faster. But there is one thing we need to mention is the non-maximum suppression. So we will find many potential candidate bounding box. And there is a technical non-maximum suppression to get the clean output of the image. So basically, we will first find the box with the greatest confidence or greatest probability for class, and then remove the other box or remove the other box with the same class with LU greater than threshold. Basically, we first find the most confident box, and then remove all the others with a significant overlap between with this box. So the model is very similar to AlexNet, but they designed the model so that it can be run very efficiently. So, and there are several iterations of this. There are a lot of details. I don't think we can go through all of them. But the idea here is they want to try many other different things. Essentially, this is kind of, now we have this framework, and then let's try all the other tricks to see which actually work, which doesn't work. Yeah, so I don't think we have time to go through all the details. But the idea here is in any development of the deep learning algorithms, usually it's not only valuable to like say, okay, here is a new method, here is a new structure. It's also valuable to study that given everything we already know, what actually really matters, and what will happen when we combine those techniques together. And in many cases, because like you probably know, at each CVPR nowadays we have 10,000 submissions and 2,000 papers accepted only at one conference. And of course, there will be many ideas that kind of proposed in parallel. And the goal of this YOLO tool is to see that given all the ideas people have proposed, let's see like what will actually happen and what for the single stage method. And then after just say tuning all the like tricks that we already know, we can already get a much better performance than all the other things and form a very good baseline for the future development. So periodically, those kind of house cleaning will be very helpful for the computer vision research community. So it's worth mentioning that nowadays, when you look up online, there are many YOLO. Like there are YOLO V1, V2, V3, V4, V5, V6, I think V7 or something. Yeah, so, and it's no longer the original YOLO or not by the same team. It's just for the namesake. So, and sometimes it can make the method more popular. But I would suggest to give your own method a more informative name than naming it YOLO V something. But there is another method called YOLOX. They have the right idea. Yes, maybe you can have the YOLO Max or something. But for YOLOX, they actually, again, this is kind of a house cleaning work. They actually did not publish this anywhere in a conference. They just say, okay, we did the work, and then we put it in an archive to share with the community. But we do learn a lot of things. One thing is, for the single stage method, we do not need to use the anchor. And they also use decoupled head in the sense that they use one model to predict the class, the other another head, another model to predict bounding box location. And they find that it's actually helpful. And what's more interesting is the strong data augmentation. I will show some more information there. Okay, so here is the like multi-head. So in YOLO, usually we use the same feature to predict both the object classification and where the bounding box is. But in YOLOX, it's found that it's a good idea to have a two separate branch or two separate small network to predict both class and the bounding box location. This is actually also related to multitask learning. So in some cases, when we put two tasks onto one feature map, then they can conflict to each other. Sometimes they help each other. And just in this case, it turns out that the classification and the regression, bounding box regression, are two conflicting tasks. And also there are many tricks. Here, the data augmentation is interesting. So when we get a deeper model and the model have more capacity, the bounding box, the object detection data set is falling behind in the sense that we do not have enough data to train the model. And one thing to combat that is to do data augmentation. For example, we can rotate the model, we can say crop it, we can flip it, or we can change the color. And even more than that, we can do mix up. Basically, we overlap two images together, or we can cut mix. Basically, we can cut one image and then paste it on the other image. And also do mosaic, or like put the image side by side and put them into a large image, put them into a larger image, like all those things. So what we found is not only those augmentation becoming kind of standard protocol for training state-of-art detection models, they are also have a very interesting implication for the other tasks. We will actually discuss them later in this lecture. Okay, well, if you're interested in numbers, though they show, well, this is basically kind of a library part. like what will happen when you put a different ingredient together, and then they provide a very thorough study for the whole thing. So of course, all those methods are based on convolution models, and now we have transformer, and it's also changed the scene of detection slightly. So remember, in transformer we have two types of structures. One is the simple attention. The other is multi-head attention, in which we first pass the token into some linear layer before we calculate the attention. And the one thing we can, this is the original transformer structure for long-range study. So when in image classification, we are only using this part, like the encoding part. So we only pass the input tokens into a multi-head attention and to a feed forward. We were not using the decoder part in the sense that we are having different Q, KQ, and V. But in detection, that turns out to be an important ingredient. Just to say that again, in classification, we are only using this encoder part. We are not using the decoding part. But in detection, it turns out that we can also find the decoding part useful, which actually gave us the DETR structure. So in DETR, we first still use the convolution network to extract image features. And then they will give us image, like some downsample image features, like downsample by 16 or 62. Then we can use those features as tokens directly. After that, after we have the token, first we can pass the token into a transformer encoder, just like what we did for the vision transformer. And the interesting part is the decoder. So in the decoder, we take the output from the encoder, and then we first learn an object queries, and then pass them into use as the Q. So in the encoder, we are using the same image feature for both V, K, and Q. But in decoder, we are only using the input feature, image feature for V and K. But for the Q, we are using the learn query. And the query is essentially learned in the sense that we can randomly initialize them, and then use backpropagation to learn that what is the best query here to encourage the decoder to produce the right object class and the bounding box. So this is the new idea of DETR. Just to say that again, we can still use the image multi-head attention to encode image feature, but we can learn a query for the decoder. In the end, we can decode the class and bounding box. If you ask whether is this strictly necessary, no. Does this help? Yes. And does this have other implications? Yes. So there are many other following up work utilizing this structure, utilizing the learned query to do like more, say, performant object detection. Okay, just to some numbers to show that it's actually working. And then here is some visualization of the self-attention. So you can see that if we take a feature here, is indeed attending to the same object. And if we take the point here, it's also attending to the same object. So this basically illustrates that the attention mechanism is able to find the pixels or group the tokens with same semantic meaning and then aggregate information together. Okay, let's summarize our discussion for object detection. Basically, based on convolutional networks, we have single stage and two stage detection. And recently, with the availability of the transformer structure, we also have DETR, which utilizing transformer to learn object query and then predict the bounding box location, the classification. All right, so now on the image, we talk about how we extract the object features, or how we extract the image features, and then also how we can locate the objects. So the natural next thing to do is that when we consider the video for 4D scene understanding, how we can connect the same objects on different frames, such that we can know their motion, at least on the 2D domain first. Yeah,
question, like you mentioned a little bit on anchor in like YOLO. Can you like explain Maybe again, over your time, please. Like you mentioned a little bit on like YOLO X, and then they remove like anchor. Can you explain a little bit on like anchor-based and anchor-free object detection?
Yeah, that's an interesting question. Once up, like several years ago, I think around 2019 something, there was a huge interest in the field. And there is also a religion war on whether we should have anchor. Like there are many methods try to kill an anchor. Also, many methods try to save anchor. I would say now is a little bit hard to say. Anchor may not be very elegant in the sense that it's kind of pull the feature in a very naive way. But in other hand, if it works, then it would works. So it doesn't really matter in the real application that whether we kill it or not. And especially now we are more and more using the transformer structure, then there's no anchor at all. Okay, so if there's no other question, then let's move on to object tracking, which basically move detection from images to videos and detect the objects in a spatial temporal domain. So object tracking has been a very long-studied problem in computer vision, and it has many applications. So not surprisingly, there are many flavors of object detection. And here in our case, we are in particular very interested in multi-object tracking. So in multi-object tracking, we do not know the particular object we are going to track, but we know that we know that which general category we are interested in. For example, in the driving scene, we know that we want to track vehicles, we want to track pedestrians, such that we know that where they are and to avoid hit them. And in multi-object tracking, so there is actually very mature pipeline. So if you just want to get it to work, say several years ago, then usually we do tracking by detection. Actually nowadays we still do tracking by detection. So we will first find the objects on each individual image, which this is actually very natural. So if we know that we want to track all the cars, then first step we can find all the cars on all the images, or at least on the images you have seen. Then the next component is to do motion estimation. This step is to propagate the objects from one frame to the next, especially to track the objects on the new frame. And we can use many different types of motion models. And we do not have to be fancy here, actually. So some work even find that just by assuming objects do not move is a very good prayer or very good assumption. So, and then on the new frame, we will have two sources of information. One information is like the motion, and we know that where the objects are from the previous frame and where the objects are on the new frame. Then based on the overlap, we can find some similarity. On the other hand, we can also use similarity, of course. We can check that whether the two persons look the same or two cars are the same. Based on those information, we can do a post hoc optimization. For example, we can use concurrent matching, which is a very classical optimization method. And we can also use some more fancier method based on graph neural network. Essentially, here we want to optimize on a bipartite graph to figure out what is the best matching between the object we have seen and the objects we see on the new frame. Since not everybody is working on tracking, I want to give you some like more illustration on the process. Let's say if we want to do tracking on this very busy street, then just make the case a little bit simpler. Let's say we just want to track the persons on the foreground, and this is the first frame. We first detect all the objects on the first frame, and then on the second frame, we first detect all the objects. All the persons on the foreground, and then propagate the objects on the first frame to the second frame. So you can see that it already look messy, And then for each pair of frame, we will build some connections. Here, I just draw some arrows to illustrate that we have connections between each pair of green and the blue box. And this connection is built by both the motion similarity, like a spatial similarity based on motion prediction, and also based on the appearance. And after that, we can do optimization to figure out that, okay, the identity of the objects or association of objects on the first frame and on the second frame. So this is still many state-of-the-art methods are using those components. And the one question I want to ask is, does this need to be this complicated? The reason for this question is when we have those many components, especially motion estimation or association optimization, it's actually prevent this kind of the moment that we are designing our manual features. Like in the classical sense, we are designing our filter to extract the feature from the image. And here in the tracking, we are manually design our motion model and manually design the association optimization. So my question here is whether we can simplify the method such that the whole thing can just be learned by a single convolutional network or by a single deep learning model, such that the model can digest like large amount of data instead of limited by our manual design. And to understand this, let's play a small game here. Again, so we want to track the image or track the objects on this image. And instead of propagate them into the next frame, let's just put them aside so that you do not know where they are on the original image. You only know that what they look like. And here is the new frame. So the game is let's color the bounding box. So what will be the color for this bounding box? Red. Like there's no confusion here. So what about this one? Yes, blue. What about this one? So this one is actually a little bit challenging because this person appears in both yellow and green box. However, we know, like at least for us, we know that it's actually the person is background in the green box. Therefore, we can color it to be yellow. What about this one? I see people are shaking their head. Yeah, so exactly. It doesn't belong to any of the previously colored box. There's actually one complication for tracking. Not only we have to associate objects across frames, we have to constantly detect whether there are new objects coming to the frame, whether there are objects disappear, and even worse, whether there's some objects disappear and come back. So this is one complication of tracking, and apparently in this case, our human eyes have no trouble of handling it. And here, of course, will be green. Basically, I want to convey the idea that when we do the tracking, we actually do not do motion estimation association optimization. We just directly use like detect the objects, and then based on their similarity, we can directly call out like what is the association. Then the question here is why does the appearance provide, like in deep learning models, provide enough information? If this provides enough information, then our problem is solved. So we can just use appearance and learn the feature embedding, just like in classification, and then do the object tracking and association. So here is our observation. So in tracking, first of all, how we train the current model. Like we assume that we have this video, and we have the human labeling. Then, like in this case, we label the black car, the white one, and then use the color to illustrate the association. Then this is the ground truth. We use this ground truth to train our model. Basically, we say that the black car are the same, and the black car and the white car are different. Basically, use this triplet or binary loss to train our embedding to express the similarity of objects. So there are apparently something are missing here. One thing is there can be many different other bounding boxes that can express the same objects. So even though that our objects are labeled by human, but we find that there are actually huge discrepancy even between human labeling. So we did the experiment before, like we have the same set of image, and we ask the person same group, two group of people to label the same set of images. And we find that the overlap between human is like 0.7, 0.8. Not mentioning that the overlap between like a machine and a human cannot beat that if we use the same ground truth to train the model. And therefore, we shall expect that when we detect those bounding boxes, there will be some small shift. And we have never considered those small shifts in our model training. And this is the same for all the objects. Another thing is like there may be misleading area in the background. And for example, if we detect any false objects in the detection, then that can be very misleading for the tracking or for measure similarity between objects, given we have never seen them before. Therefore, based on this observation, we propose a very simple method. Instead of only comparing the labeled bounding box, we first extract all the regions that are possibly containing an object. And then we put them into a joint comparison. So here, instead of comparing between one or two objects, we are comparing 1,000 or we are comparing 100 regions together, and use constructive learning to learn the feature embedding. So this actually very nicely fit into the existing detection method. Remember, this is the detection method for fast RCN. This is two-stage method. We first pass the image into a feature extractor, and then pass it to RPN to extract object regions, and then use another bounding box head to refine the location of the objects. What we can do is we can reuse the same RPN features, same region proposal features, and then pass them into a different head, embedding head. So different from the box head, here the embedding head just want to learn the similarity between objects. And the goal here is the same object, no matter which perspective, how big you are, we can project them into the same embedding. And if you are two different objects, say two different cars, even though you are two different, even though if you are both white cars, then they should still be separated in the embedding space. And that's how we express this with a constructive learning in the end. We want to contrast between the same car and between different cars, such that we can learn the feature embedding to achieve this effect. Okay, so in testing phase, if we believe that our feature embedding is very good, it can tell exactly whether the two cars are same or not, then we no longer need to turn to motion or optimization. We can just use the nearest neighbor, extract the bounding box from the new frame, and compare it into the previous previous locations or previous detected objects, and measure their similarity and see that whether those are the same vehicles or not. All right, so the real world is always slightly more complicated. There are several groups of objects we need to consider when we need to handle the complexity of the tracking. The first group are the track lists that we have seen up to the previous frame. Basically, those are the cars we have been tracking. And sometimes maybe those are the new objects appear in the previous frame. Then in those track lists, we only have one object, or we only have one observation. And another thing is we have vanished tracks. Basically, those are the tracks we have seen, say, a couple seconds ago, but disappear from the previous frame or previous several frames. But we still want to keep an eye on them in case they reappear. And we also put some distractors, like some backdrops, some random objects, just to say that if any of the foreground objects match to the backdrops, then you are not matching to the existing observed objects. Yeah, so we find that immediately after we perform this, even though our methods do not use any like even we do not use external data, we can still be better than the previous like state-of-art method. And of course, when we use the same amount of data and achieve better results, our performance is better than those even use the motion information and the optimization information. And here is illustration. You can see that on this very complex scene, even though we have like people moving around and close to each other, but our tracking method is actually working quite well. So even further, we find that if we do not need the motion information and we do not need the optimization, we can actually use synthetic data to train our model. Like remember, like in detection, we mentioned that we can use strong data augmentation. We can resize the image. We can rotate, translate the image. During the dose transformation, of course, we will preserve the object location because we can transform the object bounding box at the same time. Then when we transform the object or we transform the image with the known object location, we can actually use those transformed images to train our model without using the real like video labeling. This is what we call like basically we use data augmentation to synthesize tracking pairs and then use those tracking pairs to train our model instead of using real video labels. And here's the comparison. You can see that it's very hard to tell which one is better. But one image is trained with tracking label, the other is trained only with image labels. So you can see that it's very hard to spot the difference. And on quantitative study, the performance is also very similar. And another benefit of only using appearance is robustness. So we find that comparing to the previous method, if we artificially speed up the object motion, then our methods can still like be very robust. But the methods say backtrack here. Even though the method achieve like a similar performance on high frame rate video, but when we downsample the frame rate of the video, essentially we are speeding up all the objects on the video. Then the method based on the motion can actually have to degrade very dramatically. But our methods only degrade like slightly. Yes?
Can you go back to the previous slide? I was thinking about the person with the black dress that crosses the lamp there.
Yeah,
in the front.
Yeah,
Him. If you play the video, I think when he crosses the lamp, he's not seen, but the bounding box is still able to track him through that. And I'm not like, is that image similarity or is that there?
Here?
Yeah.
Yeah, it's a similarity.
That's still similarity based?
Yeah.
Okay, thanks.
Yeah, both of them are only using similarity, but one is trained with object tracking label, the other is trained with synthetic label. Yeah, so this is just another example to show that even in the challenging case, you do not need the motion. Appearance can be good enough. Yeah, so also it will be robust to 2D motion. And also it's worth noting that 2D motion is actually very hard to model. Even the objects stop, like it's a static, it's a stop there. The motion of the object on 2D images can actually be very complicated because your camera can be moving. And then also the object will subject to perspective distortion. Therefore, like even simple motion in 3D can lead to complex motion in 2D, and depending on many like different factors. That's another way that why like modeling 2D motion is very challenging. However, we know that the success of deep learning is we need to have a lot of data. The traditional 2D tracking data only have 20 sequences. It's hard to believe that this is the golden benchmark to measure the performance of deep learning or the performance and to compare different methods. Therefore, we have spent quite some time to build B200K. It's so far still the largest scale open driving video dataset. It contains 100,000 videos, and each video has 40 seconds. And the most important thing is it's very diverse, cover different time of day, different weather, different type of scene, well, just some samples of diversity. And based on the data, I have very comprehensive labels to support different type of tasks, such that on the data we can study many different driving tasks under these diverse scenarios. And most importantly, we care about the tracking here. You can see that compared to the previous tracking data, depends on how you look at it, it's 10 to 100 times bigger than the previous ones. Therefore, it gives us more data to train and more reliable results for benchmarking. So let's see how the method actually work on the large-scale data set. So you can see that when we drive down the street by training and train the model on our large-scale data set, everything looks actually quite good. So it's very hard, from human eyes, it's very hard to spot the error. And I want to highlight, like here, this person is about to disappear. And even though it's kind of irrelevant, but this is a very challenging scenario for tracking. And you can see that this person, after it disappear and reappear, it still can be tracked based on only appearance. And our car can basically track all the objects down the road happily. And especially on the other side, all the vehicles are constantly occluded by the tree in the middle, or the separator in the middle. But you can see that our method is still working quite reasonably. And in the highway scene, when all the objects are moving very fast, our method can still work quite well here. And especially thanks to the large amount of data, we find that even in night scene, because we have a lot of night data, the model can still work quite well. Especially you can see here, this is the rider. And this is very challenging even for human eyes, but our model can spot that and track that very reliably. So we basically find that the methods basically can happily digest all the large-scale data. If I tell you that our methods work best on our own data, that may not be very convincing. But here is the evaluation on way more open data set. So they release a similar scale data at a similar time. And we see that even compared to all the previous methods, our methods have like more than 10% improvement. And even compared to Waymo's own model, we are much better. And of course, we do not want to stop at only tracking the common objects. We also hope that our method can handle like the area objects, basically the object in the long tail distribution, not only the commonly seen objects, but also the rarely seen objects. However, we find that there are actually some interesting challenge when we extend the tracking method from common objects to the objects of in the long tail distribution. Because when we're tracking the objects on the street, if we know that the two objects are different category, for example, one object is a car, the other object is a person, then we know that we do not need to associate them together. Because if there are two categories, of course there are two identities, they are not same object. However, when we care about the object in the long tail distribution, then the classification becomes much more noisier. And then this classification will no longer be a very reliable filter for to narrow down our matching candidates. So on the other hand, we observe that actually in this filtering scheme, we do not need to know that whether two objects are which objects the exact category. We only need to know that whether the two objects are the same category or not. And potentially this can be much simpler. The name exactly the same, given the exact name. And especially, even better, this can potentially generalize to the object we have never even seen before. Basically by learn to spot the important feature for different objects, the generalization of this type of model can be much better than naming the exact category. And later, after we track the object across multiple frames, then when we look back, we have a better chance to tell the category of the object clearly. For example, if you want to tell the breed of a dog, say you want to tell whether this is a dog is an Eskimo or is a Husky, then probably if you look at the back, it's very hard to see the category. You only have to see the face. And then if you see the video, you can first find out which frame have the most significant feature, and then propagate that category to the other frames. Potentially, this can give us a better chance to classify the objects correctly. And that's exactly what we do. We will first design a module called class exemplar module. So basically, it tells us that whether the two objects are the same or not. This is actually based on the idea that is published in the before deep learning. There is a work called exemplar SVM before deep learning, and we find that idea quite influential. And then even in deep learning age, we can still use the same idea, even though we no longer use SVM. And in building the actual model, we first localize all the objects without the categories. Basically, you can think of this to detect the objectness. Basically, you find all the objects, even though we do not know what the object is. And then after we find all the objects, we use our module to group the objects into several groups. And the goal here is to make sure that the different groups will have objects of the same category, even though we do not know which category it is. And then we track within the group, and then tell the exact category. So we find that the module is not only working well in our own method, like say the QD track, it's actually also helping for the other methods, like a deep short or tractor++. So, and even on our like straight scene data, like B200K, it's still also improving. The reason is that even though the straight scene objects are like common conceptually, say bus are common, train are common, cars are common, but they actually have very different distribution. Like in our data set, we have more than 1 million instances of cars, but only several hundreds of instances of trains. And therefore, even though we only consider several categories, but they still follow a long tail distribution. So the method can also help in this case. So even further, we want to able to handle like even stronger generalization case. Not only we want to handle like tracking the object in the long tail distribution as in the everything case. We want to handle the case of open vocabulary, which means that for many categories that we will see in the testing phase, we do not have the example or training data in the training phase. And the goal here is to generalize from the seen category to the unseen category. So here we have to re-evaluate like how we can do classification, localization, and association here. Because now classification is also becoming a much more challenging problem. Because we just do not have the data for those classes. And actually for the classification, we borrow the idea from the open vocabulary classification and detection. We use the clip model to produce the text embedding for the category that we are interested in, for both the seen and the unseen category. We assume that we have a dictionary for all the categories, even though we do not have the visual examples for those categories. And then this frozen clip text encoder can encode the text embedding, and then text can encode the text and provide an embedding that can represent the concept of those categories. And then at the training phase, we want to learn an image head such that it can produce the embedding of different categories, the visual categories into the same space. In other words, we hope that, say, if we see a car, then the embedding should be in the same space with the text embedding of the car. If we see a bus in the image, then the image embedding should be projected into the same embedding with the text. Then the hope here is that even for the unseen category, our image head can project the visual information into the embedding of that text information. Then we can basically use this text alignment or nearest neighbor search to figure out what is the correct category. So for the association, of course, we can still utilize data augmentation to train our data. even for the objects that we do not see a lot. Another interesting thing here is nowadays we have the AIGC. You probably have seen ChatGPT. You probably also have seen Stable Diffusion. Like they are providing very strong data generation results for both text and images. And for example, based on text, we can even generate images of like those impossible images. But even though they are impossible, but the image looks plausible. And we can use the same process to synthesize our tracking data as well, but it's slightly more complicated. So assuming that again, we have images and we have some labels on the image, but we do not have labels on the video. First, we assume that we have the mask of the object, and then we crop the mask out. And then we use the text description of the image to generate a new image. But at the same time, when we generate image using the diffusion method, we blend in this like a crop out image into the diffusion method, such that in the final output of the image, the target object is preserved in the final image, but the background is changed. It's completely changed. So this is like an image in painting. In image in painting, we want to we want to remove the foreground objects and then fill in the background. And here we preserve the foreground and then fill in the background. Then of course this can give us more diversity of the background compared to data augmentation, because in the data augmentation or data transformation, we do not change the image content. But in this case, we can actually synthesize new image with a slightly different content. And then putting together the method will look like this. Of course, in testing case, we only need to worry about the text and the image embedding. We do not need to consider diffusion again. And the interesting thing we found here is even though we do not use any video labels, but based on our data augmentation and based on our diffusion models, we can actually generate the result that is better than the supervised method. This basically says one thing. When you only have limited data, like in the open vocabulary or like a long tail distribution case, in this case, it's just impossible to label hundreds of videos for each category or for each concept. Then the synthetic data approach can actually be a very promising approach and can basically beat the supervised learning approach when you do not have a lot of data. But of course, in the case that you want to only track cars, where you can have millions of examples, then the supervised way can still give some real performance gain. Okay, here is some summary for our basically appearance-based tracking. It's easy to scale to diverse environment and very easy to generalize to new concepts and robust to different motion patterns. And we can train them with only images. And there are many ways of synthesizing the data such that we can avoid using human labels to train our tracking data. So it's worth mentioning this actually can be very important. So when we label B200K data, like each sequence has 40 seconds, and then we sample the frame with like 200 frames. To label those sequences, it takes a skilled worker 10 to 12 hours to label one sequence. So if we do not need to spend those efforts, they actually a big relief for the human efforts, and also make it much easier to scale our data and our model to larger scale. Okay, so so far we can find the bounding box on images, and we can find the bounding box on videos, and know that the correspondence of the bounding box. And of course, in many applications, that's not good enough. We also need to find the exact pixels of the objects on the images and the videos. And that's basically the instant segmentation task. So in instant segmentation, there's actually also a very mature method called the mask RCN. And it's based, as the name suggests, it's very closely related to faster RCN. Basically, after we crop the feature, for each object. We not only predict their bounding box location and the classification, we also predict the mask of the objects. And of course, predicting the mask of the objects will require more careful sampling of the pixels. And therefore, in this case, instead of doing ROI align, instead of doing ROI pooling, we are doing ROI align. So remember that in ROI pooling, if our bounding box is not aligned with the, say, feature grid, we just shift the box to the nearest feature grid, and then use that shift location to extract the features. But in ROI align, we, instead of shift the box directly, we will, say, do some feature sampling from nearby pixel locations. And then here we basically do a bilinear interpolation to figure out, to get the feature for each location. And of course, here we are also looking for higher res pooled features, such that we can get a better sampling of pixel and therefore get a higher quality mask. So here is an illustration of this process. So again, in ROI pooling, if this is the desired bounding box, the blue one is the desired bounding box, we just shift round it to the nearest box that is aligned with the feature grid and extract the features. But in the ROI align, what we do is we will first, let's say this is our grid, and we will first subdivide the grid into smaller box. And then for each bounding box, we will do, for each small box, we will sample the feature from nearby feature grid, and do that for all the, regions. And here to have better features, instead of doing maximum pooling, we usually use average pooling here. So even though that we are still missing a lot of information, but the instant segmentation results is actually quite good. So there are many good examples of this. Basically, without deep learning, it's very hard to imagine that we can achieve results like this, which is segmenting all the objects in the complicated scene and figure out both the identity and the segmentation for all the objects. However, even though the max RCN is very successful, and if you want to have some instant segmentation, you can just grab it off shelf and then use it. But it still suffers the quality problem. So for example, in this image, we are not capturing the boundary of this object very clearly. And it's the same for all the other objects if you squint your eyes. So essentially, at a high level, all the masks make sense. But if you really want pixel level accuracy, then mask RC always falls short. So apparently, this is due to the severe feature downsampling, which is a necessary trade-off. So even if the original object has, say, 100 by 100 pixels on the original image, or even bigger, but we have to first resize them into to smaller grid, such that we can use it to supervise the feature extracted by ROI align. And this feature is usually 14 by 14 or 28 by 28. And essentially, this looks like this. Let's say we have an image like this, and we already extract the object like this. And what we do is we first divide the image or the ground truth into 28 by 28, and also downsample the ground truth annotation. So you can see that in this process, even on the ground truth, not only we are missing the information on the boundary, even worse, we are missing the information on some small area, like the leg of the bird. So this prevents us from getting very accurate information for the objects. Maybe for some application that's not necessary, but for many applications, especially for, say, AR/VR application, where you want to crop out the objects carefully and then do additional augmentation, those pixel alignment can be very jarring and can be quite consequential in the downstream applications. And to solve this problem, we take a very direct approach. We call it incoherent region prediction. Basically, we look at which information is lost in this mask downsampling, and then predict that directly. Let's say this is original mask, and then this is a downsampled mask. We just take a difference between these two masks. Of course, we first upsample this mask with a naive method. Here is just nearest neighbor sampling. And then we take a difference and we get this mask. Basically, the origin region shows that which pixel actually lose the information or actually are inconsistent with the low resolution downsampling. And then we come back to the lower resolution, says that if you segment your image with this resolution, you have to look into those pixels, because underlying those pixels, there are different segmentations. You cannot predict segment them with a single segmentation. So here is an illustration on the real image. Let's say on this resolution, we first predict that okay, those are the regions that need to look into or need to break down, and then predict a higher resolution segmentation. And of course, in many cases, maybe we need a even higher resolution prediction. And here's the interesting property of this. If a region is coherent at a higher level, then it will be also coherent at the lower level, which means that if we want to further break down the pixels for even higher resolution prediction, we do not need to look at the other pixels. We only need to look at the pixels that were incoherent in the upper level, and keep breaking down until you get the desirable resolution. Essentially, we break this image down into a chord tree structure, or represent the image with a chord tree structure. And we can obtain the structure even with only ground truth. It's kind of model independent. And then we can predict segmentation on the chord tree structure in the sense that we do not need to predict, like we do not need to pay the quadratic computation. We want to have a higher resolution. But at the same time, we can have the same quality. If you are interested in exactly what we are doing in the model, here it is. The model is very straightforward. But one thing worth mentioning here is to predict the refinement of those pixels, we have to turn to transformer, because those pixels no longer have the spatial coherency. And what we do is we extract the feature for each location and treat them as tokens, and then use a transformer just to learn the feature based on those tokens, and then predict the segmentation for each token. All right, let's see some results. This is the original result for the mass RCN. And here is the comparison result of previous methods to try to refine this. And you can see that our method can achieve, indeed achieve better results. And here is the progressive refinement process. Here is the coarse mask, and here is a high resolution, even higher resolution, and even higher resolution. You can see that gradually we can get the pixel details better and better. And this is the same process. So it's also worth mentioning here that our method has no assumption about the topology of the objects. Some other methods assume that, say, you only have outer boundary of the objects, and then we detect those boundaries and then do refinement. And then if there is a hole in the objects, then those methods can fail. But our method has no assumption about the topology of the method, topology of the objects. For example, in this case, where you have a hole in the mask, our method can still refine properly. And even further, we can extend this into video, like use the same procedure on video frames, such that we can get video instant segmentation. And one question here is, when we put all those, what we do here is actually quite straightforward. We just take all the incoherent region from all the frames, and then can count them together and then do the temporal refinement. One thing is whether the model is indeed making use of the temporal information. And it seems that the answer is yes. So for example, if we look at the attention for this particular point, the attention is spread out on all the frames. And if we look at the top 10 points of the attention, they are on not both the current frame and the adjacent frames. So it says that the model is actually aggregating information from multiple frames in order to refine the segmentation on the current frame. And then another interesting thing we find here is because labeling video mask is very challenging. Like I mentioned that labeling bounding box on video is very expensive. But of course, it's only getting worse if we want to labeling mask. And therefore, some of the previous data sets kind of sacrifice the labeling accuracy on the mask in order to label many videos. And our methods can actually refine, can actually getting better than the human labeling, and then still give you very accurate object mask. So here are some more illustrations comparing to the other video segmentation. You can see that on this case, we can get the sharp boundary for the wing of the eagle, and also for the claw. And this is another example. So basically, on just many cases, we can see numerous examples where our method can help. And sometimes that may not be clearly evaluated or justified by the benchmark either because of evaluation issues or because those small details does not take much weight in the overall evaluation. But indeed, visually, we are getting very good results. And here is another demonstration on the street scene. You can see that our methods can also work on this complicated scenario. All right, so speaking of segmentation. Okay. Yes?
Hello. Yeah. So far, I think the object tracking is very impressive, and I just wondering, like in terms of this field nowadays, are we able to already track high-speed objects? Is that still a challenge?
There are still many challenges in this case, especially in two directions. Actually, I will discuss those two things. One thing is how we can train a foundation model, like generalization. We do not want to train a specialized model. We want to train the model that can work on all the videos. Another is the data requirement. We cannot afford to label all the millions of videos. When we label the B200K video with the segmentation tracking, each video take 40 to 50 hours. Basically, one person needs to spend the whole week with some actual work to label one video. Apparently, we cannot have millions of people working on working on those, and the data is still a big challenge. And that's why the following discussion is on how we can possible method to address those issues.
Thank you.
Hello. Yes. I noticed that since the beginning of the tracking models, many of the methods requires separate optimizations. I wonder how much of it is totally separate and how much of it is end-to-end that you can put in one framework and train in one go.
All the methods we are having here are trained together.
Okay.
Yeah. So there is, even though I describe them as separate components, but they are trained together.
Even if it's transfer model and fine-tuning?
Fine-tuning? What do you mean by fine-tuning?
I mean, you mentioned, there's many parts that you mentioned that we have to have a backbone network.
Oh, yeah. Those are always trained with, say, we just take the base model, train on internet something.
Have you heard of polygon RNNs?
Yes.
What do you think about polygon RNNs with respect to some of the methods we spoke about?
It's a very interesting method. Yeah, not sure what to say about it, but nowadays people do not do that anymore. We actually invest a lot into that and see what they can work. Yeah, but there are several people for polygon. It's just very hard to track all the points, and the point for the polygon for each object is also highly ambiguous. So we find that the model along that line also have trouble to deal with those ambiguity.
Okay.
Okay, let me continue. So a small digression. Nowadays, everything is foundation. So you probably heard foundation model here, foundation model there. It's indeed affecting a lot about how we are doing research these days. But in a nutshell, what is foundation model? So foundation model can be any model that trained on broad data set, like especially in language domain. Like we can train on trillions of tokens on data and with self-supervision. And then the model can be adapted into a wide range of downstream tasks. For example, Google trained a model called POP. It has 540 billion parameters. So basically, what they found is while we are scaling up the number of parameters, then the model become more and more capable, and be more and more, and we can solve more and more complicated tasks. So that is the interesting finding, and that's why basically people are very interested in foundation model. One thing is it has so many tasks at once. Another thing is there are many emerging properties of those tasks. Basically, not only the model can help us to solve the task at hand, but also present us some properties that can be used for the other tasks. And at the same time, foundation model have many amazing applications, especially in language understanding. For example, we are offered the box of ChatGPT. I hope it's certainly a global phenomenon. And recently, there are many other companies trying to catch up and do the same thing. So people are quite excited about the prospect of language model, large language model, and what they can bring us to improve our productivity. So usually in foundation model, we have three components. So we need a lot of data, and we need a lot of parameters, so it's a very large model, and we also need a very large amount of compute. So in computer vision or even in broadly machine learning, we usually do not concern ourselves with compute. But indeed, there are many people that are working on how we can interconnect many GPUs efficiently, such that we can train the large model. And there is a famous report by a Stanford researcher, and they call the foundation model a paradigm shift. So this is not a word we use lightly. So especially for people who are highly conservative. And here's actually very interesting observation. I saw a lot of rejected papers in the CVR neurons that they say that we are proposing a new method, which will become a new paradigm. So this is one clear signal that you will get rejected. Yeah, so that's just basically overclaiming your contribution. Usually, it is just like saying some word is for to describe things that happen in the past, not for the things happen in the future. So paradigm is also usually used to measure the name for the method that is proposed in the past. That we observe that indeed this method or this procedure can be used again and again, or we use it, and then we can call it paradigm. Well, given that, when people say that it's a paradigm shift, then indeed it's something very significant. So, of course, every computer vision researcher are curious, what is the foundation model for computer vision, since it has made a big splash in language. So essentially, it's breaking down into several areas, several questions, like how do we get the data, and how do we organize the pipelines. Click is a very promising candidate, like we use Click for the overall hybrid object tracking. However, like computer vision is much more than just naming things on image. It's about modeling relations, getting object location, and also get more complex, solve more complicated tasks. So recently, as you some have probably heard, like we have segment anything, which is a very significant advance in foundation model. Basically, it's a foundation model for the dense predictions or like instance segmentation. And the major contribution there is they can label 100, like 11 million images with more than 1 billion masks. And then they can train a very big model on hundreds of GPUs. And interestingly, how they organize the parameters seems to be very simple. They just use a vision transformer to train on the model, nothing fancy. And the key part is how they can obtain the data. First of all, they actually bought the data from everywhere in the world. That sounds easy, but labeling the data is very challenging. We will discuss a little bit later. And the model they present is basically a simple weight model with some prompt. This prompt is similar, very similar to the object query we discussed in detail or in the transformer method for object detection. Basically, in this case, we can encode different type of prompt or different type of input, like a point, box, a mask, or a description, and then basically project them into a vector, and then combine those vectors with the image encoding in a cross-attention fashion to get the final mask or get mask what you want, or mask of what you want. So in this case, it can unify many like segmentation masks. So in another way to look at this, so we have image encoder and we have decoder. So the encoder is just a vision transformer, and the decoder is a attention structure to combine image and prompt encodings. Like again, similar to how we do object decoding in detail. So the most important part of this is the data engine, like how we can label all those data. So apparently, it's infeasible to ask people label 11 million images and label every object on those images. So basically, they break down the image, the labeling into 3 parts. The first part is assistant manual labeling. The other part is semi-automatically, and then fully automatic labeling. So in the manual labeling case, basically, instead of the user to draw polygon or to draw mask, the user or the labeler will just click foreground background points to say this is foreground, this is background, and then the model will try to figure out what the mask will be for the foreground objects. And if the model is not doing a very good job, then the user can also have the option of using brush and eraser to edit the mask. However, for the purpose of editing, due to the preference of scale, like labeling a lot of data, they have a limit of how much time an annotator can spend on each mask. So if the mask is too complicated, then the data engine will say, okay, forget it, let's label the next image. So therefore, the mask quality can already be a label, can already be a problem in the first stage. And in the second stage, we just rely more and more on the trained model to help us to segment the image. And therefore, it's impossible to annotate all 11 million images with fine details. And not surprisingly, the model trained based on those images cannot capture the fine details. And again, so we are interested in like the detail, like high quality instance segmentation. So what we found is we indeed have a much smaller, finely labeled data sets. Some data sets actually depend on synthetic data, like not really human label. And the question here is whether we can get the best of the both worlds. Basically, we want to have the generalizability of a second anything model. And also we want to have the details that can be learned from those small data sets. we have a naive try. Say we collect all the detailed data set together, and then say we first evaluate the SAM. And this is the performance we can get. And then we fine-tune the model on the detailed labeled data. We get a much higher performance, and the visual experience is indeed much better. So this is very good. It means that the SAM is the width structure, even though it's cropping the 16 by 16 patch, it's actually contain a lot of detailed information about the image. And by fine-tuning it, we can train the model to capture those small details, which is great news. However, here's the bad news. So the SAM has a very good performance on COCO, which is a common used instant segmentation dataset for the common objects. After we fine-tune the model on the HQ high-quality data, the performance on COCO become miserable. So this says that although fine-tuning can give us better performance on the details, but it loses the generalization capability it should have for segment anything. So how can we solve the problem? We add another branch called the HQ SAM. So the idea here is let's freeze the original image encoder and the decoder for the original SAM, but only add a small component such that we do not screw up the generalization capability of the SAM model. And then we add additional component to learn how to fine-tune the details. And in the end, we merge them together to form the high-quality mask. And here is the result. So you can see that indeed, after we do our own processing, first of all, we can get very good performance on the fine details. And at the same time, we can still preserve the performance on COCO and even improve them, because now our method can not only work better on those, still can work on those objects, but also recover the small details on those objects. And here is basically the evaluation on the generalization. And I believe this is the COCO evaluation. So you can see that instead of having a worse performance, we have a higher performance compared to the COCO trained model. And we can also train the model with very lightweight, like say the model you want to run on mobile. I find that our method can still improve the both quality and generalizability at the same time, give you the option, depending on your computation budget, you can choose the right model of right size. And we find that this model is actually currently working the best on segmentation in the wild. And here are some illustrations. You can see that it indeed can provide some high quality mask. And even on COCO, so we can improve, say on the general object segmentation, we can improve the segmentation quality. And here is another experiment on the video segmentation. And this is yet another data set. All these results is to say that not only our model can give you higher quality segmentation, but it preserves the generalizability of the model such that it can work in a very diverse domain. Okay, so this is good. So it says that we can get a very good image segmentation and can work in any scenario. And one key enabler of SAM is the point-based editing. And we were wondering that whether we can extend this labeling method to videos. Basically, when we're labeling the video mask, whether we can only use point instead of using polygon tracking, which can be very expensive. So the answer seems to be positive. We combine the state-of-the-art point tracker with SAM, and then do mask propagation in the video domain. And here is an illustration. So for example, we can assume that the user clicks on points and representing foreground, background for different objects. And then our method, combining with SAM, can track those objects across the videos. So this basically says that it's possible to do same point editing and labeling for videos such that we can label a large amount of video segmentation mask, but with very low cost. And here is a segmentation on different domain. So again, thanks to the generalization of the SAM, we are able to handle segmentation, video segmentation on different domains. And the points here are the query we put into the process. But this, of course, is not always working. This is a failure case. You can see in this case, it's very hard to tell the change of the water and overall the ocean, and therefore the segmentation does not work. In this case, we will need some more human involvement to fix the segmentation. So we want to be more aggressive here. Even though that we show that we can use the same point labeling to label the video mask, but labeling the video mask is still very expensive and take a lot of time. So can we avoid labeling the video mask at all? Like only do bounding box on images and use that to do both 2D tracking and segmentation tracking. So ideally it could be true so that we can cut our labeling costs dramatically. And it seems that it's also possible, especially on image. There are many works on weakly supervised image segmentation. Like basically we can learn segmentation from like bounding box labeling on images. However, when we use those methods on videos, we observe some temporal consistency issue. Even though on each image, we can hardly see the artifacts of the labeling. But when we play them on the video, because human eyes are super sensitive to small jittering or small change of the pixel, and then we can easily see the degrading of the artifacts of those segmentation if we do not use full supervision. At the same time, this can also be a very good opportunity because we can use temporal consistency as a supervision to train the model. Say that even though we do not have the labeling on the video, but the temporal consistency itself is a good supervision signal. And here is how we can utilize the temporal consistency. Say on the first frame, like given a patch, we want to find out where it is in the next frame. Usually you can turn to optical flow to do the task. But optical flow itself is very hard to generalize. And training the optical flow method itself that can work into in video in the wild is quite challenging. And therefore, instead of relying on optical flow, we do a very simple method. We assume that for each patch, it won't move far on the next frame. And let's say assume that it's within this 5x5 range. And then within this range, we find the top K similar patch, or find the patch correspondence satisfying certain constraints. Then we assume that across the frames, if the two patches are similar, then they should have similar semantics. So, for example, if the patch is a horse, then on the next frame, it should still be a horse. And if the patch is a person, then on the next image, it should still be a person. And then we can use this as a supervision signal. So in the process, we do not need any human labeling. Here is the result. So here, this is the segmentation only on like using images, and this is the ground truth labeling, and this is our results by combining temporal consistency and image-based labeling. So if we zoom in, you can see that our method is actually quite good and well aligned with ground truth, while the model trained only on images can have some obvious artifacts. And here is another demonstration. So let me emphasize this again. When we get the results, we do not use any mask, either on videos or images. We only use bounding box on images to train the tracking and the segmentation. And then you can see that we can depict the contour of the person or the object quite accurately, even though that on some small parts, like the parts, let's say on the leg of the glass or on hair, we still cannot deal it very well. But we are already very happy since we do not use any mask to get this. Okay, so here is a brief summarization for the segmentation. So now from bounding box we can get pixel level labeling, and our pixel labeling can generalize well to like a very large domains. So now let's try to lift our 2D estimation to 3D. So seeing depth in 3D is actually an impossible task, in the sense that so the object can be any size. Like even for the same image, I can say that this is your Barbie home. Like this, like we are seeing a miniature sofa, such that the depth can be very different. However, human eyes suffer the same illusion. Like there are many illusions saying that, for example, they confuse you about object size and the depth, and play with some very interesting effects, and make you realize, okay, you're actually fooled because they make seemingly similar objects in the real world, but actually something very small, or something very big. So, however, even though human eyes have this bias and can be easily fooled, but human is learning some useful 3D bias such that we can survive, and we can perform useful tasks. Like we can drive with our 3D perception. We can use tools with our 3D perception, even though that we do not have the active sensing. So if I ask you, like how many millimeters is the chair from me, then it's impossible to tell. So we want to do something similar with the computer vision task. Even though that is impossible to learn, say, given any image, we know all the exact depths. But we hope that with the commonly seen objects or scenes, common scenes, we can have reasonable depth estimation. And what we do here is, usually we learn, we learn the depth for each individual pixels. But what we propose here is, instead of learning the depth bias for each pixel, we propose to learn a bias for each group of pixels. Like the groups can be pixels on the same objects, or group pixels on like objects of similar depths. So in this case, by aggregating information from multiple pixels, then the model will have easier time to learn the bias and predict the correct depth. And worth noting that when we do the grouping, we are not turning to any external supervision. We are not using object mask to supervise the grouping. We are learning the grouping in an unsupervised fashion. And the goal here is we learn the grouping such that it can predict better depth. And you can see that indeed the grouping makes sense and reasonable. And here is another illustration of the results. So on the left is the ground truth collected by LiDAR. On the right is our master result based on only single image. So you can see that the my computer is getting sluggish at the end of the day. Yeah, so you can see that the depth predicted by the single image is actually look like very plausible and well aligned with the ground truth. But we have like denser depths because we have more pixels than LiDAR scans. And here is another illustration of this process. All right, so this tells us that we can indeed learn some useful 3D depths from single images, and how we can apply that for the object level. So that's basically what we consider as 3D object tracking. So we can build a very simple baseline based on everything we have learned. So we can detect the objects and extract region features for each object. And then for each object, we can predict the depth and the rotation angle, basically predicting their 3D features. And when we have multiple frames, we can use our tracking method to connect objects across frames. And even when we have more frames, then we can use 3D motion estimation to help us do the tracking. So you may ask me that, wait a minute, I would say you were saying that motion is not a good idea for tracking. Then why in 2D, 3D tracking you want to use motion? There are two reasons for that. One thing is, I mentioned that 2D reason is very hard to model, but 3D motion is much more easier to model. If a car is stopping, then it's stopping in 3D motion. And most of the objects in 3D world are having either constant velocity or constant acceleration, or we won't get too much, we won't be wrong too much. So the 3D motion is much easier to model. Another thing is 3D motion is necessary for a lot of downstream tasks. For example, if we want to predict where the car will be in the future, then we will need to predict the 3D motion and know where the car come from in the past in order to predict their future trajectories. So therefore, it's also a necessary component in the whole system. Here are some other things to notice when we do this type of 3D projection. For example, we can represent the object center back into the 3D, but the 2D bounding box center is actually can be quite far away from the 3D object center. So for example, due to perspective change, the 2D object center can be slightly different from the 2D object center. However, when the object is truncated or occluded, then the 3D object center is very far away from 2D object center. So we can now simply use the 2D like bounding box center as the replacement for 3D object center. Another thing is we can use 3D motion nicely to help us to do the tracking. So for example, when we detect those three cars in the image, and then the middle car may disappear or occluded in some frame, then we can keep sliding the objects in 3D, and even when it reappears, we can know that where it is in 3D, and then know that where it can be on 2D domain. It's just a lot of things we can make use of in 3D in order to help us to do better tracking. For example, we can say that when we do object association, the object order should be preserved. So it won't happen that if object was 100 meters away, and then suddenly it becomes 1 meter away. So this 3D coherency should be preserved in doing association. When we put all those things together, so here is a demonstration. You can see that in this very complicated intersection, our method is actually tracking all the objects very reliably. On the left is perspective view, where we project the 3D bounding box into 2D images. And on the right, we show the top-down view of all the objects in 3D. You can see that the layout can be well modeled by our method. And again, so we can train on large-scale data and even handle the challenging dark scenarios as well. So even further, on many self-driving cars, we not only have like a single view, we have surrounding view. When we have surrounding view, there is actually very interesting property. We mentioned that the object can go out of the image and come back, and that can be very hard to detect. So even when we have the panoramic view, the scenario actually changed. We know that the object will never disappear unless it's occluded. So we can use this clue to help us to do better tracking. So essentially, when we have multiple views and they have some slight overlap, when we detect the bounding box or track each individual cars, we can first track the cars across the camera, and then find their association across the cameras, and then track the cars, across different frames to find out their trajectories in 3D. So essentially, for the tracking on panorama views, we can first track objects across the cameras and then track them across different time steps, such that we can achieve more reliable tracking. And here is another demonstration on the Waymo open dataset. You can see that this person is transitioning smoothly from one frame to the other. And yeah. So one thing I want to mention here is we actually see that there are a lot of things to study here, and we are observing very rapid progress in this field. So for example, when we first do our 3D object tracking, we see that we can achieve 5 times performance compared to the previous method. And this year, we can achieve another 10% improvement. You know, like nowadays, if you work on detection or segmentation, like a 1, 2, or 3 point improvement can already be quite significant. But we still observe like a very large progress in this like very important area. So another thing is saying that maybe at near future, we will see a convergence of camera-based methods and LiDAR-based methods, and show that we can indeed only rely on camera to do the 3D perception. All right, so last, this is more like a future perspective, and therefore I do not have too much to present here. A lot of things still need to do to go from, like go in one step further. Like now we can say get image feature, get 2D location, and get a video tracking, and we can get segmentation, and then we can lift everything into 3D. But how we can do even one step further to get all the shape information from the objects. So one thing I want to mention here is called a neural radiance field. Some of you may have heard of it. So the idea is very simple. Let's say, assume that we have many observations of the same object. Then for each camera, we can shoot rays into the 3D scene. And then we can say that at each location of the 3D of the ray, what is the radiance? So if it's occluded, of course, the radiance will be just the object will be like something non-existent. And if the point is on the view, then we can say that, okay, it's the object appearance. And if it's in front of us, then it can be something like different. So the goal here is to learn a model, what we call a neural radiance field, that can given a 3D location or given 3D ray location, then we can predict that what is the RGB color in this location. Like that's all you need to know. Here we have a method, given a view, and given a 3D location from that view, we can know that what is the color in that view, in that particular location. And then from this function, we can recover the how an object look like from different views. So for example, in this case, we can render this, we can say learn from many different views, and then render the toy cart like from different views. And here are some more demonstrations. So we do not have that many views in the training data, but you can see that after we learn the function, then we can say change the viewpoint arbitrarily in the 3D environment, and then generate new image. And because we have the new image, and we are having multiple views here, then we can also recover the depth, or essentially the shape of the object as well. So in other words, so nowadays to represent the shape, we no longer need to say represent the shape based on mesh or based on voxels. We can represent the shape based on implicit representation, a field, a function. And then if you want to query the view or want to query the shape, we can query the function to recover whatever information you need. So this is a very good representation of the 3D. So, and here we can put everything we have learned together. So there's a work called panoptic neuron field, which is essentially combining everything we have seen here. We extract feature from images and detect all the objects, and then segment the objects and stuff, and track the object in 3D. And then for the objects, combining the segment and the tracking, we can use nerve for each object use nerve to represent the shape of each object. And then we can do to get the reconstruction of all the scene, the whole scene, or even do re-render in the whole scene. Here is here is a diagram. So basically, from the video, we can say segment the objects and track the objects, and eventually get the depth, get the depth, get the instant segmentation, semantic segmentation, and object level information. One thing we can do is we can query from the model to get the results for each task, say segmentation, depth, or like a scene decomposition. And one application, and of course we can play this in the video domain. One interesting application is scene editing. If we have all the information, all the representation for the whole scene and for all the objects, for example, we can insert a bus here and say play it naturally in the environment. But I have to say this is still this field is still not that mature yet. It still require a lot of work. That's why we spend a lot of time on the image encoding and the detection, because it's kind of stable and it won't change probably for the next 5 to 10 years. But for a lot of other things in 3D, especially for putting everything together to get the neural representation for the whole scene, the research just gets started. Okay, with that, that concludes our discussion today on 4D scene understanding.
Anyone have questions for the speaker? Okay.
I think everyone is good now. No question anymore, I think.
I guess my questions would be more like asking for advice. You mentioned there's a lot of things that keep on changing, especially the last part. Do you have any advice for researchers working in this field on should we focus on the thing that's already stable, or should we move on to the thing that's currently, it might change soon, so the effort that you put in, it might be a waste eventually?
Yeah, it's hard to say, just like it's hard to predict what will happen in the scientific field. But let's say it won't be wrong if you work on something important but receiving unfairly less attention. But at the same time, even though image encoding and detection has been quite mature, but to really solve the problem still require several significant breakthroughs here, and we do not know what they are yet. And just like in image encoding, we thought that convolutional network is all you need. And then later we have this transformer structure. So it's very hard to predict what will happen. So working on those tasks can give you the potential benefit of having those big breakthroughs, such that everybody can utilize your result.
Okay, thank you. And does anyone has any questions? My other questions would be about our segmentations, the refinements around the borders things that you did, and you mentioned that there isn't really an evaluation method that can properly evaluate how well that is doing. Do you have any insight on if we have to make a benchmark about that? How would that look like?
Yeah, there are several benchmarks. There are also evaluation metric focusing on the boundary quality. So it's a very hard problem to do it perfectly well. Because even if we can evaluate them, only focusing on the boundary region, but your ground truth may not be that good.
Yes,
so in the end, we have to rely on both quantitative evaluation and the qualitative evaluation to see that whether we are obtaining significant improvement.
I see. All right. Thank you so much. Yeah, can we have another round of applause?
Sorry, we have one more question. A late one, but it's okay, it's okay.
I started to lose you around the topic on foundation model, but I think it is a very important topic So I would like you to explain more of. So what I'm not understanding is that you say that foundation model has to be trained on broad data with self-supervision, but in the segment anything model, I don't understand what are those self-supervision, what kind of training data that you need again.
That's a good question. So foundation model, when they say yearly self-supervision, is in the bracket. So it's not a saying for sure, not saying for all. It's just like for language, it's yearly self-supervision. And for vision, there are many efforts to explore self-supervision for training foundation as well. So, but in the case of segment anything, it's taking a different approach. Instead of relying on self-supervision, they rely on this like learning with human in the loop. Basically, how use the model to help people label the data, such that in the end we can use the data for fully supervised learning.
So it's not really self-supervision in that case?
No, it's not.
So you
It's
require
not at all.
human levels?
Yeah, it's not self-supervised learning at all.
I see. So then, is that considered foundation then? I thought that self-supervision is like a requirement for a model to
Yeah,
be
so the
foundation.
definition of foundation model is very loose. But as long as you can convince people that your data is dramatically large than anything else, and also the model can generalize into like many domains, then you can claim it's a foundation model.
I see. So the definition is not quite clear yet.
No,
What is
there's no
considered
clear definition.
foundation? I see. Thank you very much.
Okay, and I guess that's the last question. So, one more. Okay.
So yeah, thank you so much for like a very impressive presentations. And can we have like another round of applause for the speakers? And after this, we'll have our welcoming party on the sixth floor. So we can, fifth floor, on the fifth floor. So we can move on there.